everyone. My name is Jaroslav Ruby, and I'm working as an application engineer at Vibration Research Corporation. This presentation is focused on multi-axial testing and basics of multi-axial testing. It will be a little bit of technical talk, how to perform, let's say, multi-axial tests and what are the needs to perform them. So, we may start the presentation. And first of all, we will talk about common testing equipment that is needed to perform multi-axial testing or uniaxial. Well, the testing equipment can be divided for equipment for uniaxial tests. That means that we are using mostly electrodynamic shakers, which most of our people know pretty well. If we will take a look on a picture on the left, we can see uniaxial electrodynamic shaker, which is described as a SDOF solution. That means that's a single degree of freedom solution. We are testing the equipment in three independent perpendicular axes. So that means vertical axis, which is Y, and horizontal axis H1, H2. H1 and H2 are there because generally if we are trying to, let's say, test the equipment, we have to, let's say, turn it for another horizontal axis about 90 degrees. So the test is performed, let's say, in horizontal axis 1, in this direction. Then we will turn the equipment around 90 degrees, and we are testing it in horizontal axis number 2. Then it's placed into the vertical axis. Unlikely, the multi-axial tests that are described over here are performed mostly on servo-hydraulic devices. We can see on this picture a multi-axial testing machine described as end-of solution, which means multi-degrees of freedom. The axis H1 is describing to us, let's say, horizontal axis 1, H2 horizontal axis number 2, and V vertical axis. These testing machines are performing the test simultaneously in all three directions, or in one direction, or in two directions, depends on the requirements. In general, we may say that to operate the multi-axial shake table, we must have a knowledge about tests on uniaxial testing devices. So if you have a basics on testing on uniaxial testing devices, then you can perform multi-axial tests way more easier than without knowledge of these uniaxial tests. If we will go to another slide, we can see how the tests are divided. So for single degree of freedom solution, it's uniaxial tests, most common and basics. A lot of labs are having these electrodynamic shakers or servo-hydraulics, or we may have pneumatic actuators, and also, let's say, electric actuators. Depends on a, let's say, problem we are solving in the lab. Then, on the other hand, we have multi-axial tests. And as I was saying before, we can do, let's say, 2 degrees of freedom simultaneously, 3 degrees of freedom, or 6 degrees of freedom. Multi-axial tests are less common. They are used for specific purposes. So, in general, we are using them for road simulations in automotive industry or seismic tests. The test can be performed on ED shakers. It's not so common, mostly on servo hydraulics, or you can have, let's say, multi-axial testing on shake tables powered by electric actuators these days. Electric actuators are some point in the future, but most of these testing devices are under development. If we, let's say, take account the performance of electrodynamic shakers and servo hydraulics, which are mostly used for testing, there are big differences because in general on ED shakers you can perform tests in a broad frequency range up to 2 kilohertz or 5 kilohertz, depends on the shaker. We can obtain large accelerations around, let's say, 100 Gs. We may obtain, let's say, very, very big shock events in the meaning of 200 Gs, 300 Gs. The disadvantage of these shakers is that mostly if you are trying to, let's say, simulate a motion with a big amount of displacement or velocity, there is a problem because mostly the displacement on ED shakers is around, let's say, 1 or sometimes 2 inches, depends on application. For the servo hydraulics, the situation is different. The frequency range is commonly up to, let's say, 100 hertz. We can find systems to 200 hertz or sometimes 500 hertz. Depends on the manufacturer. We can obtain large displacements, large velocities, but obtaining high accelerations such as 100 Gs, it's a problem. Same is valid for the shock. When you are performing multi-axial tests, it's way more difficult than providing the uniaxial ones. Because mostly you are dealing with cross couplings and other things, and the design of the machine is way more complicated for the multi-axial tests. Before we will start with multi-axial testing, let's talk a little bit about uniaxial tests. Are they easy? Is my knowledge of them good enough to run multi-axial tests? Those are the questions we need to have in our heads, because mostly uniaxial tests are sometimes very, very difficult to perform in a manner of, I don't know, testing on different acceleration levels in different frequency ranges, etc., etc., and the equipment is usually acting at the low level excitation linear, but on a very high excitation levels non-linear. This can be seen on these graphs. So the graph on the right is showing us resonant frequency surge of this specimen placed on rubber isolators. So for this resonance frequency surge test, we were running, let's say, random vibration loading at level or excitation level 0.5 GRMS. From this, you can see that the structure is acting very, very nice. There is no nonlinearity over there, and everything is so-called perfect. We may also, let's say, calculate the resonant frequencies, Q values, dampings, and as we can see, there is no nonlinearity. Unlikely, we can, let's say, perform uniaxial test through sine sweeps, and on this graph, we can see how the structure acts nonlinear at every different level of acceleration excitation. So if we will have the same 0.5 G as here, I must say that, let's say, the input motions are different, we obtain linear response. If we are increasing the acceleration to 1G, 3G, 5G, and then 10G, you can see how the structure is acting nonlinear. This is a thing that needs to be known before performing every test, uniaxial, multi-axial, because generally, if the structure is acting nonlinear it will have, let's say, different effects on a shake table motion than if it acts linearly. This knowledge is basic for, let's say, multi-axial test, because then the problem is not only uniaxial but multi-axial, and this nonlinear behavior has a significant effect on let's say, simulated motion. This video is showing us performance of uniaxial test on a servo-hydraulic multi-axial testing machine. The aim of this video is to show how, let's say, the structure underneath the shake table is influencing, let's say, the behavior of the shake table and everything in the lab. Mostly the structure underneath the shake table is a concrete structure on metal springs. This property of the, let's say, seismic isolation of the underneath the shake table is very important, because at some point, if the properties of the seismic mass underneath the shake table are tuned badly, we may run into the significant problems. Here we have another two videos. The video, let's say on the right, is showing us performance of uniaxial test on an ED shaker, and the test is focused on, let's say, verification of properties of 3D printer and the printing quality. The input motion that is put, let's say, to this test, it's random vibration. And in general, on the video on the right, we can see that, let's say, the printer is in a steady state condition to investigate resonant frequencies. And let's say left video, we can see the printing quality. So we have a triaxial accelerometer placed on a printing head, and we are observing how the head, when it's moving, it's acting underneath the vibration loading. On this slide, we may see another type of test, because mostly you are using electrodynamic shakers for performing, I don't know, environmental simulations of transportation events or other things. This is a specific design of the test when we are using electrodynamic shaker as a fatigue machine. This test was to verify 3D printed hoses for special applications. Mostly these tests are performed to verify how these 3D printed hoses are acting under a random vibration environment. The hoses are pressurized, and the test is running for several hours, something like 36 or maybe 50, depends on application. And as a last example, we can see on a picture on the right, uniaxial tests on a servo-hydraulic testing machine of flexible shear beam container filled with sand. This test was done because in general we were working at CU Boulder with Dr. Marabuchi on soil behavior under shock loading conditions or transient loading conditions, and we were investigating the parameters of the soil under different conditions. So we were using different types of containers, we were investigating the stiffness of the soil, and also we were investigating the properties of the containers themselves. On the video on the left, we can see the test of the laminar container, which is a very specific type of container, and this container is simulating in a most realistic way the behavior of the soil. We can, let's say, see on the video on the left how the empty container, the laminar container, acts under swept sinusoidal loading. So, as we were seeing on this video and the videos before, uniaxial tests can be performed in different ways, in different frequency ranges, with different equipment installed on a shaker. In general, these tests are not easy to perform because mostly, let's say, we are testing different structures with different behavior, with different stiffnesses, and it's always good to know at some point the dynamic parameters of the structure. And this is the main aim of the uniaxial test, because when you are performing multi-axial tests, before you are doing them, you need to somehow understand the behavior of the structure. So you are performing these uniaxial tests, let's say a random vibration excitation to investigate the resonant frequencies, swept sine motion to do the same. You are, let's say, increasing the levels of the motion to see how the structure acts under different loading levels, and this gives you the necessary information to perform multi-axial tests. So let's start a little bit with the multi-axial tests. As we can see on the picture on the right, this is a picture of an airplane, and it's only describing to us what kind of motions we have in reality. This is an airplane, so it's not valid for, let's say, test perform in automotive industry. So this is mainly focused on, let's say, yaw, roll, and pitch. Unlikely for automotive testing, we are also playing here with the translations, not only rotations, but translations. So in general, we are doing at some point 6 degrees of freedom testing. We can see it over here. So we may have multi-axial shake table. Here is the test jig, here's the specimen under the test, and we have different type of motions that can be performed through the multi-axial testing device. So translation in one axis, translation in second axis, translation in third axis, yaw, pitch, and roll. So in general, on a multi-axial testing machine, we may perform different types of tests, different types of simulated degrees of freedom. Everything depends on what's the purpose of the test. But this is only the basics. So here we can see, let's say, performance of a very, very easy seismic test. We are having, let's say, 9-ton specimen on a shake table, and on a picture on the left, we can see what happened to the specimen after the seismic test. So here, everything is so-called perfect. The structure is a little bit complicated because all these elements are made from steel, and in general they can slide on each other. So the purpose of this test was to verify, let's say, the performance of the shaker with this very, very specific specimen. On the picture on the left, you can see what really happened. So all these blocks were sliding, and at some point, this was a very dangerous test, but for an engineer that is investigating properties of the shake table and how you can control the motion and how, let's say, the behavior of the testable specimen is acting on a control system, it's very, very important. Here is a video of that. So as we were seeing on the video, the structure is sliding, it's making, let's say, motions that are in a realistic testing unwanted. But on the other hand, this gives you a lot of information. The test performed was a seismic test. It was a triaxial test, and we were using specific motion which is used for devices installed on nuclear power plants. So if we will take a look at the motion is specified by required response spectra with different types of dampings, because mostly when we are performing the seismic tests, we are using earthquake levels on an operational basis earthquake and safe shutdown earthquake event. From these required response spectra, we are generating the time history signals, which are an input for the tests we were seeing on a previous video. Performing these tests is a little bit difficult because mostly you are using very, very strong motions in a manner of large displacements, large velocities. And when you are testing some electronic parts, you are also having very, very big amount of acceleration that is simulated. But this is only something as an example because this topic is very, very huge, and to understand it, you need to have a huge amount of knowledge about IEEE standards, seismic qualification procedures, etc., etc., also assay codes and other things. So this is only a very, very brief example how these things could be done. We may say that performing the seismic test is at some point one of the most easiest multi-axial shake table tests. Unlike, let's say, 6 degrees of freedom test. So, from this, we may jump on a multi-axial test performance. And we can see on a picture on the right, multi-axial test of a vehicle body part. These tests are performed in 6 degrees of freedom. The same thing is for the picture on the left when we are testing a bicycle carrier system and it's fixing to the vehicle rooftop. These tests are very, very hard to perform, and in general you need to have a huge knowledge about how the multi-axial system works and its performance. Mostly these tests are performed in a time domain. So previously when I was talking about ED shakers and uniaxial tests that are performed on them, we are mostly using their motion, something like random vibration, motion. In general, it's a white noise, swept sinusoidal motion, combinations of the motions, shock motions. Sometimes you are using, let's say, data obtained from the field. But with replication of these signals, we are mainly using only the data obtained in the field, and we are trying to replicate them in a time domain. On ED shakers, mostly we are investigating everything in a frequency domain. Since we are doing this in a time domain, it's very, very difficult to, let's say, have the motion that we want on a shake table. So if we are doing the simulations, we are trying to match the realistic conditions obtained from the field. But this is very, very hard in the time domain. On this video, we can see how the 6 degrees of freedom test is performed. This test is for bicycle carriers, and it's a durability test. So this was an example on how these tests are performed in laboratory conditions. Well, it looks pretty nice and it's pretty cool to perform these tests. It's fun, but before doing such a test, you need to prepare the data for it. And it takes a lot of work to do such a thing because in general, you obtain some data from the field. You can see that you may have this type of signal. Then you have to edit the signal. So in the next step, you are getting rid of the parts of the signal which are producing small amount of fatigue. These data are in acceleration. But you also, before doing the editing, need to do investigation of the signal in a manner of velocity or displacement to see how the signal is acting. So mostly, if you will only focus on acceleration part and not the velocity one or displacement one, you may get rid of signal parts that could be very, very important in a final simulation. So once again, this is the real signal, this is the edited signal. Then you are performing some filtration on a signal because generally the testing machines have some parameters that you can perform the test, let's say from, I don't know, 3 Hertz to 100 or 5 Hertz to 500, depends. So you are then performing filtrations, you are comparing the signals together, then you are, after, let's say, preparing the signal for the machine, replicating the signal, and in general, you are investigating in the first step what is really happening in there. So mostly one thing is to prepare the signal, second thing is to simulate the signal in a proper manner, and then you are doing the investigation, everything together. Where are the nonlinearities? What is happening over there? Because mostly if you are doing multi-axial testing, the stiffness of the system placed on a multi-axial shake table plays a very, very important role. If, let's say, the structure is not stiff enough, you will always have problem to obtain the right motion. But now I am talking about replicating the motions in a time domain, which is very, very common for servo hydraulics. If you are doing this in a frequency domain through random vibrations, the situation is way, way more easier. But in general, cover all these topics, how these tests can be done and everything needs a special type of presentation. So, as I was saying before, you are comparing the data in time domain, but not only in the time domain, but you are investigating for those acceleration time histories showed on a previous slide, parameters such as amplitude distortion. So you can see it, the amplitude distortion between every signal over here. You are investigating computed power spectral densities. So you can see over here how the filtration acts on a power spectral density function generated from the acceleration time histories. You can see how the editation is acting on power spectral densities, how, let's say, everything is simulated. So these comparisons are very, very important. Same goes for rainfall count performed for every individual signal, and also level crossing. This gives you all the necessary information that you need to know about how you manipulated the signal before the test and what kind of signal you are obtaining from the test. The last step that is performed is computation of potential damage produced by, let's say, signals that are simulated on a multi-axial shaker. So this is a graph we are using, let's say, for computing the potential damage for bicycle carrier testing. I will not talk about it in a, let's say, depth manner, because it's very, very complicated how you are obtaining this and how you have to manipulate the signal, because mostly, let's say, these values are the values that you want. These are somehow edited and simulated values, and before performing the test, you have to match everything together by strategies like increasing the amplitude of the simulated motion to obtain, let's say, the damage that was lost by filtration or whatever, and also you are elongating the signals. But this needs another type of presentation which is showing all these strategies. In general, multi-axial tests are very, very complicated to perform because you are playing with a lot of signals. You are playing with stiffness problems of the tested structure and everything. And in general, the aim of the multi-axial test, mainly for, let's say, these bicycle carriers or roof carriers, is to replicate a signal in the most precise manner, which is super complicated. Vibration research has many tools how you can, let's say, prepare the signal or how you can replicate the signal, but in general, everything depends on how you want to do it. Mostly for ED shakers, the solution, how you can replicate the data, is at some point easier than if you are doing servo-hydraulic testing. So this is all from me. I hope this presentation makes some sense, but honestly, if somebody wants to perform a multi-axial test, it takes a lot of time to understand almost everything that is tied up with this testing. You have to sit many, many hours with the machine, and at some point, there is no manual that will tell you, put this value over there, put that value over there, hit the start button, and it will be running. This is not happening. Sometimes you are running in many problems regarding the stiffness and everything, and that means that in general, you know, the control is impossible. You have to reconfigure all the system and everything, change the filters and other related things. And in general, maybe multi-axial tests are cool, but on the other hand, it takes a lot of knowledge to perform them in a somehow precise manner, because the data are mainly compared in time domain, which is at some point way more difficult than you are comparing only power spectral densities between each other. So this is everything from me, and have a good day.